Right, we're carrying on with this radioactivity sheet. Now go to the top and have a look at two important things. Yeah, unit of activity is the BQ or Becquerel, and half-life is the time taken for 50% of the radioactivity to decrease. So this is one definition, right? The decrease. So just learn that. Them are two important points. And whoa, we know what an isotope is. So let's write that down because I think that comes up as well. It's good for chemistry anyway. Isotope. Atoms of the same element. Atoms of the same element with same number of protons, but different number of neutrons. The good thing about this definition is it cuts across chemistry as well, so let's stick with that. Right, done. Right, okay. Carbon 14 is a radioactive isotope. Right, look. This tells you how many protons you've got, and it defines the atom carbon. This tells you how many protons and neutrons. How do you work out the number of neutrons? It's the top number minus the bottom number. So it's 14 take away 6, which is 8. They've called it nucleons. Okay, the number of nucleons, the number of neutrons. Wait, hold on. Okay, they've said 14. So the word nucleon equals protons plus neutrons. Let's make a note of that. That I did not know, but I do now. Because I'm bare clever. So nucleons equals protons plus neutrons. Right. Let's keep going. Right, okay, so number of neutrons would be 8. And number of electrons, right. Number of electrons in any atom equals the number of protons. And we know the bottom number is here, the proton number, yeah. So we're looking at 6. There you go. So electrons equals protons in any neutral atom, or all atoms are neutral. Okay, when carbon 14 decays, it emits a beta particle. What is a beta particle? It is an electron. So let's go write that down. Oh, okay, isotopes there. So saved us writing that. So we're writing a beta particle equals an electron. Okay, got that. Happy with that. Right, okay. Carbon 14 has a 5,700 year half-life. You started off with 6 grams. What mass of carbon will remain after 11,400 years? Oh, okay. Oh, okay. So what they're saying is after 5,700 years, I've got 3 grams. and then after another 5,700 years I've got 1.5 grams, because these two added together equal 11,400 years. So it'll be 1.5 grams. So that's how they did it. Right, what is an isotope? Atoms. So how they've defined it is like this. Look, atoms with, then again, with the same proton number. Oh no, let's not use that. Let's not use that. That would be silly. That we're making stuff up. With the same number of protons or atomic number, yeah. But let's stick to this. But different number of neutrons. That's the definition they've given. All we put in front was this. Atoms of the same element That's all we did. Right, okay, good. Let's move on. Right, there are different types of ionizing radiation. Oh, there you go. This is a good one to keep. An alpha particle has a charge of +2 because it's a helium nucleus. It's a helium nucleus. A helium nucleus is am I confused? Or is that true? Right, give me 1 second, I'll double check that. Yep, it's a helium nucleus. It's 4-2. Right, okay. Right, beta particle is an electron, so it's got a -1 charge, and it's got a very negligible, small mass. And gamma ray has got no charge, and what is it emitted by? Unstable nuclei. Okay. It's good to know that, actually. So let's do that. Let's do that. Let's take a snapshot of this and revise this. Right, let's have a look. Right. Right, the diagram shows a machine, aluminium foil, not aluminum, aluminium. So aluminium will stop beta and alpha, but not gamma. Right, so that will be a, that will have to be a, oh, I don't know. Yeah, gamma rays will always go through, so that's useless, and alpha particles, none will go through, so that's useless. So you have to use beta, because if it's thin, it might escape it. If it's too thick, it'll give a low reading, so then you can adjust the rollers. Right, okay, so explain why beta particles are used. So remember what we said, right? We said alpha particles are stopped by a sheet of paper. Beta particles are stopped by an aluminium sheet. And gamma rays are stopped by lead sheets. So why is it that we use beta instead of alpha? Right, okay. First of all, alpha particles would not penetrate or go through metal sheet. Gamma would all go through. Would all go through. They would penetrate through. So no useful reading on the thickness. Right. With beta, if the foil was thick, beta particles not many beta particles would go through, giving a low reading. And then if foil was thin, a high reading would be obtained. So that means that then you need to adjust the rollers accordingly. Right, okay, that's cool. Right, radioactive source contains strontium-90. Strontium-90 emits beta particles, so we know that's an electron. To complete the equation, so we need to know, so look at this, whatever, let me do it this way. So the mass overall should not change here, right? So that should still be 90. That was 38. If I put 38 and then take away 1, it's going to go to 37. That's no good. So we can't do that, yeah? So it has to be 39, because 39 minus 1 is 38. Alright, so this is more like a maths question. Just balance up the charges and masses on both sides. Well, sorry, more masses. Which of these describes what happens to the strontium 90 when it emits a beta particle? Right. So what's happened to the number of protons there? It's increased. So the number of protons increases. The number of protons, no. The number of neutrons, no, because the neutron decays to give a proton. So look, a neutron will split up to give a proton and an electron. So these two charges will cancel out, and that one there is neutral. Number of neutrons increases, no. Okay, we're happy with that? Right, okay. Right, let's just stop there and we'll do the next one.